All right, let's dive right into this explainer and unpack a 2,000-year-old scientific detective story about the fundamental building blocks of our reality. Everything you interact with, the screen in front of you, the coffee cup on your desk, your very own body, it's all made of atoms. But how we understand the structure of these atoms has changed so drastically over time, it's honestly like trying to build a house while the laws of physics keep rewriting your blueprints.
Looking at this evolutionary timeline, it's wild to see the full roadmap of this journey. It's a history of scientists repeatedly drafting, testing, and ultimately tearing down their architectural blueprints of the atom. We start off with this perfectly solid, indivisible sphere, and by the time we reach the modern era, we're dealing with a mind-bending, blurry quantum cloud.
To make sense of this incredible evolution, we're going to hit 6 distinct phases: shattering the solid sphere, the solar system flaw, stepping onto the staircase, the quantum cloud, the cosmic address, and finally, blueprinting reality. Let's get into it.
Phase 1. Shattering the solid sphere. So, let's start with the longest-held belief in the history of science, the idea that the atom was an unbreakable solid object. Think of it like a microscopic billiard ball that just couldn't be broken down any further. For millennia, we trusted this concept of the uncuttable particle. But then, J.J. Thomson's 1897 cathode ray experiment completely ripped that illusion apart. By applying high voltage to glass vacuum tubes, Thomson actually extracted something even smaller from the atom, the negatively charged electron. I mean, imagine realizing your solid billiard ball is actually leaking tiny, highly energetic pieces of matter.
Now, because atoms as a whole have a neutral charge, Thomson knew those newly discovered negative electrons had to be balanced out by something positive. To explain this, he drafted our first new blueprint, famously known as the plum pudding model. A great everyday analogy is to just imagine the atom like a chocolate chip cookie. The negatively charged electrons are the chocolate chips, and they're just embedded within this uniform, positively charged, spongy dough that makes up the rest of the cookie. Which brings us to phase 2, the solar system flaw.
That cookie analogy explained the neutral charge perfectly. But, as with all scientific blueprints, it was about to fail a major real-world test. Enter Ernest Rutherford and his famous gold foil experiment. Rutherford fired heavy, positively charged particles at a microscopic sheet of gold foil. If that cookie dough model was correct, those heavy particles should have punched right through the soft pudding like a bullet through tissue paper. But the shocking reality? A tiny fraction of them violently ricocheted straight back. This proved the atom isn't uniform dough at all. It's actually 99.99% empty space with an unimaginably tiny, incredibly dense nucleus sitting right at the center.
This groundbreaking discovery gave us the solar system analogy, which is probably the one you've seen everywhere. It proposed that electrons orbit that dense central nucleus, exactly like planets orbiting the sun. But there's a fatal flaw here. Classical physics dictates that a charged particle constantly accelerating in a circular orbit has to radiate energy. And as it radiates energy, its orbit shrinks. Calculations showed these orbiting electrons should spiral into a self-destructive collision with the nucleus in just 10 to the negative 8th seconds, literally an instant collapse.
So, we move to phase 3, stepping onto the staircase. Because atoms obviously don't instantly self-destruct, otherwise we wouldn't be here having this conversation, scientists realized the old rules of classical physics were fundamentally broken at the microscopic level. They needed a totally new kind of physics. The crucial pivot here is altering how we think about energy. In classical physics, energy acts like a continuous, smooth ramp, right? You can stand at any possible elevation on a ramp. But this new physics requires us to think of energy like a staircase. You can stand on step 1 or step 2, but you simply cannot exist in the empty space hovering between the steps. The physicist Max Planck solved the radiation problem by proposing exactly this. He argued that energy doesn't flow as a continuous wave. Instead, it's absorbed or emitted in discrete, indivisible packets called quanta. Think of it like buying milk at the grocery store. You can buy 1 gallon or 2 gallons, but the store is never going to sell you a continuous, infinite stream of milk down to the microscopic drop. Energy comes in distinct, fixed chunks.
Niels Bohr took Planck's concept and applied it directly to the atom's architecture. He proved electrons don't spiral into the nucleus because they aren't on free-falling ramps, they are locked onto specific, fixed orbits. Think of them as being stuck on the rungs of a ladder. An electron can only absorb or emit light when it makes a sudden, instantaneous quantum jump from one rung to another. They physically cannot exist in the space between the rungs, which totally prevents that death spiral into the nucleus.
Let's pause for a second and look at how this builds. We started with the plum pudding cookie, which solved the neutral charge but completely failed the gold foil test. That gave way to the solar system model, which discovered the nucleus but was mathematically doomed to instantly collapse. And then we arrived at Bohr's really elegant quantized staircase, solving the stability issue. But science never rests, right? Even Bohr's model had a fatal flaw. The math only worked perfectly for hydrogen, and it totally ignored a very strange new concept called wave-particle duality.
Phase 4. The quantum cloud.
The era of classical physics officially ends right here. Those neat, organized models of the past, thrown out. Our scientific detectives were forced to embrace a much blurrier, far more bizarre reality. They had to ask a radical question. What if our fundamental assumption that an electron is a tiny, solid particle moving along a defined path is just completely wrong? Because if you zoom in close enough, the very concept of a solid particle begins to completely unravel. Enter Werner Heisenberg and his famous uncertainty principle. He proved mathematically that it is physically impossible to know both the exact position and the exact momentum of an electron at the same time. A great analogy for this is taking a photo of a speeding race car. If you use a super fast shutter speed to get a crisp image of exactly where the car is, the tires look still, you lose all the information about how fast it's moving. But if you use a slow shutter to capture the motion blur to see its speed, you no longer know its exact position. Because of this reality, Bohr's predictable planet-like orbits were exposed as a fiction. To solve this, Erwin Schrödinger developed complex math that completely rewrote the blueprint yet again. He discarded the strict planetary orbit entirely and replaced it with an orbital. An orbital isn't a set path, it's simply a mathematical probability cloud showing where an electron is likely to be found. Imagine a swarm of bees buzzing frantically around a hive. You can't track the exact path of any single bee, but you can clearly see the dense, blurry cloud where the bees are most likely spending their time. That is the true reality of the atom.
Phase 5. The cosmic address.
But here's the practical problem. Even inside a chaotic, blurry cloud of probability, chemists still needed a precise way to map out and locate these electrons so they could understand how elements react. So they created what we can think of as a cosmic address system using 4 quantum numbers. Locating an electron is just like finding a friend's house. Step 1, the principal shell, is like finding their country. It tells you the overall energy level. Step 2, the subshell, is finding their specific city. That determines the 3D shape of the cloud. Step 3, the magnetic orbital, is their street, telling you how the cloud is oriented in space. And Step 4, the spin, tells you exactly which house on that street they live in.
And finally, Phase 6, blueprinting reality.
Now we bring all these abstract rules and probability clouds together to build the physical, tangible world that we interact with every single day. The amazing thing is that this seemingly chaotic, blurry probability cloud is actually governed by incredibly strict internal logic. As atoms grow and add more electrons, those electrons don't just fly around randomly. They fill up the available space following a very specific architectural schematic.
3 golden rules dictate this organization. First, the off-bow principle. Electrons build from the ground up, always filling the lowest energy orbitals first, exactly like a bricklayer building a wall from the foundation up. Second, the Pauli exclusion principle. No 2 electrons can have the exact same 4-part cosmic address. If they share an orbital, they must have opposite spins, like 2 people sharing a park bench but sitting back to back. And third, Hund's rule. Electrons prefer to occupy their own empty space before pairing up. It's very much like strangers boarding an empty bus. Everyone sits in separate rows until every row is taken and they're finally forced to sit next to someone. These 3 rules determine how every single element on the periodic table behaves.
And that brings us to the end of our journey from the solid sphere to the quantum cloud. To wrap up this explainer, I'll leave you with this incredible thought to ponder. How crazy is it that the solid device you're holding right now, the chair you're sitting in, and the intricate biology of your very own body are all held together by a microscopic universe built entirely on blurry, invisible probabilities? Really makes you look at the physical world a little differently, doesn't it?